This lesson is on volume by revolution, and it focuses on what textbooks are going to call your disk or washer method, but I tend to either call it the perpendicular method because you're drawing perpendicular to an axis, or a CD method because when you make the shape it kind of reminds you of a CD, which is what they're talking about with disc and washer. Well, the discs that you're familiar with in this day and age are CDs. So before we go to the steps and things, I want to put the example down that I use throughout the notes. I'm going to use the same example because this process is a little bit more complicated, and it's just going to be easier if I'm using that same idea throughout, so we're not changing equations on you as well as process. So we're going to have something that's sort of like a parabola, but the equation is x cubed equals y squared, and we're going to graph it from 0 to 4 on our x-axis and 0 to 8 on our y-axis. So if you were to solve this and type this in your calculator in that little region between 0 and 4 on your x-axis, it's going to have this shape to it. We're going to call the region below the graph of x cubed equals y squared region 1, and I'm going to refer to this other region as region 2, the one above it. Now, region 1 we're saying is going to stop at 4. Region 2 we're going to stop it at 8. So that's what we're referring to when we talk about those two regions. Now, I'm going to give you the steps. You're not going to understand a lot of what I'm saying until we actually have a problem to do. So, bear with me. I have these down for a reason, because once you go back after you've worked some of these with me, they're going to make sense. And so when you're studying, these steps will make sense to you. Our first step is to draw a typical rectangle, and I'm going to do a small rectangle. We're going to draw an arrow of rotation to show how we're rotating, and we're going to draw what I call height arrows in. Then we're going to decide whether it's a dx or a dy rectangle. And I'll go ahead and tell you, if we have drawn our rectangle this way, it's a dx. If we have drawn it horizontally, so vertically, it's a dx. If our rectangle is horizontal, it's a dy. And we've done dy area in here, what I've called dy area, and we always looked at it sideways, so it's real similar to that. Then you're going to decide if you need to write one or two integrals. You're going to write one if the rectangle that we drew touches the axis of rotation, the axis we're going to rotate around. We're going to write two if it does not touch that axis of rotation. Then we're going to put limits that match dx or dy. So if we have a dx rectangle, in our case, because our x-axis went from 0 to 4, our limits will be 0 to 4. If we decide that we have a dy rectangle, our limits will be with the y-axis, which would be, in this case, 0 to 8. And again, that's going to change when problems get changed, but throughout the notes I use that same one. And then we're going to solve those integrals. So, okay, our first example, we are going to revolve region 1, which was the lower region, around the x-axis. So I'm going to sketch this again. We have x cubed equals y squared. And we went from 0 to 4 on our x-axis and 0 to 8 on our y-axis. Region 1, again being this lower axis, we're going to revolve it around this x-axis. So I'm taking this whole region and circling it around here. Now imagine if I was in 3 dimensions and I took that line and I went around, and the area in between it, so it would be a solid figure. It would make kind of a teepee type shape in 3D. The best way I can describe this is when you go to a party store and you're getting decorations, those decorations that come folded flat, but then they have like the two cardboard sides, and in the middle is all this tissue paper, and when you unfold it, it becomes like a wedding bell or something like that. If you imagine this as the folded flat, and then you unfold it, you're going to have that 3D shape. And I'll try to draw it here to to kind of show you what it might look like. Okay, so I mean, I've just sketched some lines in, but imagine this kind of a bell heel turned sideways shape. So that's what's happening. Now, do you have to be able to visualize that to get these problems right? No. You just have to understand that's what's going on. Okay, so I'm going to go back to our problem. This is the rotation arrow that I was talking about, and some of you may be able to do it without drawing that, but I always like to remind myself where I'm going, and I'm taking that region going around the x-axis. The first thing I want to do is draw in my typical rectangle. So somewhere between 0 and 4, and I usually go somewhere in the middle, I draw a rectangle perpendicular, and this is why I call it the perpendicular method, perpendicular to the axis of rotation. So since I'm going around the x-axis, I'm drawing that rectangle perpendicular to the axis of rotation, and it does not like me filling it in, but whatever. Now that I've drawn that in, I'm going to draw height arrows. And the height of this thing is just from that axis up. Okay, and I can only get one arrow in because the bottom is sitting on that axis, and I'll show you in a minute what it's like when you get two. But that is a height arrow, and I can only draw one. That will also match the number of integrals we need. The number of integrals we need is 1 because this is touching the axis it's going around. So I'm going to have one integral. Now, that is a vertical rectangle that I drew, so I know that that is a dx situation. And since it's a dx situation, I'm using the x-axis limits 0 to 4. Now, what do I put in that integral? Well, if I just take one rectangle and I revolve that one rectangle around the axis, what shape does it make? It makes a circle. And so we are going to use the area formula for a circle, which is pi r squared. That r is actually going to be what your height arrow touches, and in this case it touches the function. But if you'll notice, this function is not solved for either x or y, so we have to solve it for 1. Because I'm in the dx situation, I need my variable to be x. I need all the stuff to be on the x. So I'm going to take the square root of both sides, but I'm going to write it as a power. So this x is going to be to the 3/2 power. So this is the equation that I'm going to use for the function in this case. And that height arrow touches the function, so that is the radius, x to the 3/2. Okay? That's how you set it up. You figure out dx or dy, one or two integrals. Everything today is going to be pi r squared because we're taking rectangles perpendicular to what we go around, and they make little circles if we revolve that rectangle. The last step to solve, you can use the fundamental theorem of calculus, or you can use your calculator and do the math number 9 and let it solve. This one should be fairly easy to solve using the fundamental theorem of calculus. The first thing I would do is simplify. I'm going to take that pi out front. I'm going to do 3/2 times 2 and just get cubed. That's an easy antiderivative, and then I just have to plug in my 4 and 0 and solve. Get 64 pi. And obviously if you're doing in your calculator, you're going to get the decimal version of that. For the rest of these notes, I am going to just set it up because we have practiced the fundamental theorem and we have practiced using our calculators to get the integrals solved. So I'm going to trust that you can do that. The big thing today is learning to set these up. So for the rest of the notes, I am just going to set the problems up. You can solve them on your own if you need to. Okay, for example 2, we're going to look at revolving region 2 around the x-axis. And region 2 was this upper area here. We're still going around the x-axis. So I'm going to take this area and go around the x-axis. Now this one would be harder to imagine. It's because it's going to stop at 8, the outside's going to be like smooth, but the inside would be almost like a vase cut out. But again, if you can't see that, that's okay. Don't stress. I'm going to draw now my typical rectangle, and again, I'm stopping this at 8 because that was our region 2. And my typical rectangle has to be perpendicular to what I'm going around. So here's the x-axis, perpendicular to that, somewhere in the middle there. This would be my rectangle. Okay. Now, this time I can actually draw 2 height arrows. Because the bottom is not sitting on that axis, I can draw the height to the bottom and the height to the top of that rectangle. Because it's not sitting on the x-axis, that means I have 2 integrals. When you have 2 integrals, you are subtracting. Okay, now I've drawn in everything I need to draw in. I need to decide, is this dx or dy? Well, since it's vertical, it's dx. So both of these get a dx. And my x limits are 0 to 4. So 0 to 4, 0 to 4. And again, when I revolve just that one rectangle around, I'm going to make a circular shape. Now this one will be more like a CD because it'll have a hole in the middle, right here. But that's what you're subtracting out. That's why you're subtracting. So again, the area for a circle, pi r squared, is what we're going to use. The r's are the arrows. It's always going to be that long one minus the short one. So the long one goes to 8. And it doesn't matter where I draw that rectangle, it's always going to touch 8. So the first one is 8. The second one touches the function. Now the function changes, and that's where the variable comes in. So the short arrow touching the function, again, I need it in terms of x because we are in the dx situation. So I need all of the stuff on the x. And so that'll be x to the 3/2 equals y again. So x to the 3/2 is how I'm going to name my function for that second situation. So that is the setup for example 2. Okay, now we're going to revolve region 1 around the y-axis. Region 1 was that lower region, and we're going to go around the y-axis. So I'm taking this area over here and going around this way. That's my arrow of revolution. So if you imagine revolving that around and being in 3 dimensions, it kind of is like a bowl shape cut out in the middle, but because we stop at 4, it has like a smooth outside. I imagine like one of those wooden bowls that people make that they're straight on the outside, but then they have a bowl shape in the middle. Again, you don't have to be able to visualize it. Now we have to draw our typical rectangle, and you have to remember to draw perpendicular to what you're going around. Since the y-axis is this way, I'm going to draw my rectangle horizontal. So here's my typical rectangle. It's kind of in the middle of that region, be fine. Now your height arrows come from the axis you're going around. So I'm going to come from the y-axis and go to the bottom and the top of my rectangle. And again, sometimes things just disappear. I had to draw 2 height arrows, and this rectangle is not touching the y-axis, and so that makes us have 2 integrals again. So I'm going to have integral minus integral. This is a dy situation because our rectangle is horizontal. So that tells me I'm using the y limits, 0 and 8, and I need a dy at the end. So I'm going to go 0 to 8, dy, 0 to 8, dy. Again, because this is going to make a circle, I'm doing pi r squared. And what's making a circle is that individual rectangle rotating around. It's going to be like look like a record or a CD. Okay, so now we have to decide what the radiuses are, and those come from what our height arrows are touching. Our longest one touches 4, so that is our first radius. Our short one is going to touch the function, but again, I've got stuff on both sides. This time our variable is y because we have dy's. So I need all the stuff on the y. In other words, I need to take the cube root of both sides. Well, cube root is a 1/3 power. So I'm going to say this is x equals y to the 2/3 power. It's just another name for that function, but it has the variable that we need. So our short arrow is touching the function. That is our second radius, y to the 2/3. And that was pi r squared. I left off a square right there. So that is how we set up this problem. Now, if you were using your calculator to do this and using that math number 9, you're going to need to treat these y's like x's because that's how our calculator thinks. So just treat this as dx and this as x and dx if you're plugging that in. But again, this can be done by hand using the fundamental theorem, and this is not that bad. It's not too complicated to do. Okay, now is the time that I would really like for you to pause and try to do number 4 yourself. You're revolving region 2, which is the big fat region right here on top, around the y-axis. And so this would be a wonderful time to pause and try that one. So pause now. Okay, let's check your answers. So if you were looking at region 2, you're going around the y-axis, so here's our revolution arrow. Our typical rectangle would be horizontal, kind of in the middle of the area, because it would need to be perpendicular to what we're traveling around. And we would only be able to do one height arrow because that rectangle touches the y-axis. It's obviously dy, so you would be going 0 to 8 dy. Then you're filling in pi r squared. Your height arrow touches the function, so that would be your r. It's just that you need everything on the y, so that would be y to the 2/3. And again, this is a simple one solved by fundamental theorem or your calculator. So hopefully you did well on that. Before we go on to some other problems, I want to talk about what happens when the radius or the height arrow comes from a different place. So far, we've either had height arrows coming from the x-axis or the y-axis. And if it was coming from the x-axis, we were in a dx rectangle and we were touching the function, which was whatever f of x was. If we were coming from the y-axis, we were touching the function, but we needed our variable to be y. And we're talking about when you touch a function with those arrows. Now, if you come from other directions, okay, so that are not from an axis, which can happen, and we're going to see those next, it's going to be, if you're coming from the right, a number minus your function with the correct variable. If you're coming from above, it's going to be a number minus that function because you're coming down or from the right working toward the left, working backwards from normal things. Okay. And we'll also talk about what happens when you come from below an axis too a little later on, but this is a good thing to keep in mind before we get started here. Okay, example 5, we are going to revolve region 1 around y equals 8. Region 1 is this lower region again. Y equals 8 is the horizontal line up here at 8. So we're taking this section and going around up here. Okay, this is going to be a little bit different. So the first thing is draw correctly. Our rectangle has to be perpendicular to what we're going around. This is a horizontal line. So when I draw my typical rectangle, it's going to be perpendicular to that. It's going to be a vertical rectangle. My height arrows are going to come from the axis I'm going around. One comes to the bottom and one goes to the top. And so since I have 2 of those, I know I'm going to have 2 integrals. So I'm going to do integral minus integral. Okay, again, we are vertical here, so that's a dx rectangle. So I'm going to use my x limits from 0 to 4. So 0 to 4 dx, 0 to 4 dx. And since I'm doing just one rectangle around, I'm thinking, okay, it makes a circle, so pi r squared. Everything today will be pi r squared. Now I think about what these long and short arrows represent. Okay, the long arrow is coming from 8 down, but it's touching 0. 8 minus 0 is 8, so that's an easy one. The shorter arrow comes from 8 and touches the function. So this is the situation I was just talking about. We're going to do 8 minus our function. Our function now needs the variable to be x, so we've done this several times, be x to the 3 halves. Okay, so when we're coming from above and touching that, we're going to subtract. And technically we subtracted here, we were just subtracting 0. So this is our setup. We can use fundamental theorem or we can use our calculator. Okay, for example 6, we're going to do region 2 around y equals 8. And y equals 8 again is this horizontal line. Region 2 is this top region, so it's going to go around that y equals 8. So a typical rectangle would be in this region, somewhere in kind of the middle, and perpendicular to what I'm going around. So what I'm going around is horizontal. I'm going to draw my rectangle vertical. Now, when I do my height arrow, because it's sitting on that y equals 8 that I'm going around, I can only draw one height arrow, and that means that I'm only going to have one integral. So I'm just doing one integral. Since it's a vertical rectangle, it's a dx, we're using the x limits, 0 to 4 pi r squared dx. And then, what would this be? We're coming down from 8 and touching the function. So 8 minus our function, but what variable do we need? We need it to be x. So this will be x to the 3 halves. It needs all the stuff on it. Okay, and you may want to practice typing that in your calculator and getting that area before we move on if you want. Let's try a different kind of revolution next. Okay, so instead of this time coming from above or from one of our axes, this time we're going to come from x equals 4. So we're revolving around something different now. X equals 4 is the vertical line at 4, and it's the edge of that bottom region. So region 1, again, is that bottom region. So I should be taking that around this line. It should make a nice pointy mountain for us if we can visualize it. Our typical rectangle has to be perpendicular to this line because that's what I'm going around. So perpendicular to that would be a horizontal rectangle. And our height arrows come from the axis I'm revolving around. So I can only draw one since it's sitting on that axis. So I have one height arrow. That means one integral. So I'm going to do one integral pi r squared. Now this is a horizontal rectangle, so that's a dy, and my y limits are 0 to 8. So 0 to 8 dy. Now my arrow comes from 4 and touches the function. So since it comes from the right, I'm doing 4 minus. The function needs to have all the stuff on the y, so that'll be y to the 2/3. And that's how we set that one up. And again, solving it is not a problem for you. Or at least it should not be. Okay, now we're going to do something a little bit different. This one we're going to revolve region 1, which is the lower region, around x equals -2. X equals -2 is back here. And x equals means a vertical line, so we're actually talking about this line right here. Now, if you revolve that region 1 around that line, I'll go ahead and draw that revolution arrow in, you're going to have a big gap in the middle, and that's okay. It's just like, again, kind of like with when you have a CD and there's a little hole in the middle. So it's going to jump this area here. Now, we still follow the same process. Our our rectangle, our typical rectangle, needs to be perpendicular to what we're going around. And since it's a vertical line, I'm going to draw my rectangle horizontal. My height arrows still come from what I'm revolving around. So it's pretty far off this time. And because I had to draw two, I have two integrals. So I'm going to be doing integral pi r squared minus integral pi r squared. Now, I started to write d, but we haven't talked about that. It's horizontal, so that makes it a dy. Our limits for y are still 0 to 8. So 0 to 8 dy, 0 to 8 dy. Okay, now deciding what these are, you're coming from behind the axis. Well, from the axis to the end, we can measure, we know is normal. In this case, we're hitting 4. Well, this is still like a distance, so we went from -2 to 0 as well. So this distance is 2, this distance is 4. Our long arrow is 6. Our short arrow covers, again, that distance of 2, but then it hits the function. So I'm going to say the function, and our variable needs to be y, because we're in a dy situation. We added these together because it's that long. It made sense to add that together. You're doing the same thing here, even though it's variables. So this is going to be 2 plus y to the 2/3, 2 plus your function. So when you come from the far left or below, you end up adding lengths to those radiuses. And again, when you come from the right or above, you end up subtracting. Okay, let's talk about one more situation that's kind of weird. And in this case, let's revolve region 1, which is this lower region here, around x equals 6. So this region ends at 4. What we're wanting to do is revolve it around x equals 6, which is a vertical line out here. So again, there's going to be a gap in the middle of this three-dimensional figure, kind of like a volcano in this case, when you visualize it. Okay, still follow that same procedure. I'm taking region 1 around x equals 6. So there's my rotation arrow. My rectangle needs to be perpendicular to what I'm going around. The rectangle stops at 4 because region 1 stops at 4, and that's what we're revolving. So here's my typical rectangle. My height arrows always come from what I'm going around. I'm going around x equals 6. So come from x equals 6. Now, because these are coming from the right, the little light bulb should go off in your head and say, okay, I'm going to be subtracting somewhere. Because you had to draw 2, you know you have 2 integrals. So I'm going to have integral minus integral. They are horizontal rectangles, so that's dy, so I'm going to go from 0 to 8 and have dy's. And again, we are using pi r squared. Okay, we're going to do the long one minus the short one. The long one goes from 6 to the function. So it will be 6 minus the function in terms of y. So y to the 2/3. The short one goes from 6 to 4. And you can write 6 minus 4, or you can just go ahead and figure out that that's 2, because that's an easy one. And so that's how you set it up. So we've done stuff from above, from the right, from now the far right, from below, and from the left. So hopefully we have an example of everything that could get you going in the right direction for the problems that you're going to face. Okay, I want to talk about one more situation before we're done, and that's this really complicated situation. If you had something this complicated, a region bounded by F, G, and H, and my H has disappeared, what would you do? if you were trying to revolve it around the x-axis. So you're taking that region and going around the x-axis. Well, you would, let's say that they crossed at 1, and then these two met at 6, and then these two met at 10, just to have some numbers to plug in. So in that case, if you look from 1 to 6, you just are worrying about what's between F and G because H is not in that trapped region. So you can kind of draw a little dividing line there. And from 1 to 6, you would have to draw your rectangle perpendicular to what you're going around, and you would have height arrows for that. And that would be the integral from 1 to 6 pi r squared dx minus the integral from 1 to 6 pi r squared dx. And then the long one is touching the f of x function. The short one is touching the g of x function. That would get us the first hunk. But then you would have to figure out what the second hunk is. And if you draw a rectangle over here, it's only touching H and G. And so when you draw your height arrows to the bottom and the top, they look like this. And so we would have the integral from 6 to 10 of pi r squared dx minus the integral from 6 to 10 pi r squared dx. The long one would touch the h, the short one would touch the g. Now what are you doing between these two things? You're adding because you want the total volume of this part plus this part revolved, so you actually get a plus between those. And so that is how you would represent something that complicated. Just take it one piece at a time. That concludes this lesson.